So hello and welcome students. So let us start today's class. MA415 Algebra. And this is lecture number 33. Okay. So today we will start some idea of field theory. This is also part of the syllabus. So I will try to give some basic idea of field theory. So now recall what is a field that we already discussed, but let me recall. So a field is a triplet with two operations. So one is this addition, other is this multiplication, and the property is that with respect to addition, it is abelian group. And number two, if you remove zero element from F and then take multiplication, then also it becomes abelian group with respect to multiplication. So what does that mean? That means with respect to multiplication also it has inverse, okay, for every non-zero element. So then it is called a field, and then obviously we have the example field of real numbers, field of rational numbers. Okay, so examples. This field of real numbers. Okay. Field of reals also some people called. Field of rationals. Field of complex number. Okay, so the most common example, and then we will go give lots of examples slowly. Okay, complex numbers. Okay. So some properties we can discuss. Some properties. So for example, characteristics. If you want to know what is characteristic of a field, so field are also ring, right? So we know what is the characteristic of a ring. So characteristics of a field is either 0 or a prime. It cannot be composite integer, and that is you can check that fields are also integral domain, right? And we proved this thing for integral domains. Okay, so this is one property. And then another property you can say definition that if you want to know what is kind of that's kind of a smallest field which does not contain any other field. Okay, so that you can ask what is such kind of field. So this kind of field are called prime field. So a prime field is a field which does. Okay, so maybe I can first tell what is a subfield. Does not contains does not contain. I must say what is subfield, but you can say here contain any other field in other field. I mean, obviously f is contain f itself. Other than f, it can correspond to any other field. Okay, and if there is such field, so for example, q is a prime field of characteristic 0, field of characteristics 0. Okay, and for characteristic prime, it z not be z. Okay, so z not be z is the prime field of characteristics P. Okay, so it does not contain any other field other than the itself. Okay, and so this kind of field, see, if there are something another field inside the bigger field, those fields are called subfield. Similarly, we can define something called extension. So extension field, which is let a be a field and k be a field containing f, then k is called an extension. It can be, I'm saying n means it is not unique, right? Instead of if, and if is called a subfield of k. Okay, so extension means bigger, subfield means smaller than that. Smaller in the sense that it's contain inside that field. Okay, so like for example, you say that q is sitting inside R. Okay, it's also inside C. Okay, so R is an extension of Q, C is an extension of R and Q both. Okay, so and then Q is a subfield of R and Q both. R is a subfield of Q, R is a subfield of C, Q is a subfield of R and C both. Okay, so this is an example of extension fields, and note that. So also you can just remark, you can say that, so whenever you have an extension, so I will write down like this, k over f. So k over f means k is this means that f is sitting inside k. Okay, this is the notation. So whenever I have a field extension k over f, then k is a vector space or whatever, linear space, vector space over f. And proof is simple, because vector space over f means what? That means the property of, so you have obviously the addition of vectors is addition of k is the addition of vectors. Okay, so you remember for vector space what you need a addition and a scalar multiplication, right? So the map this k cross k to k, this is the map addition, is the field addition, that is also vector space addition, as that works also. And you have map from f cross k to k, and that means what? That is So I'm using the same notation, but it is called scalar multiplication. So you're taking an element, say alpha or a whatever, an element here from x, and this will map to alpha x. See, remember alpha is also element of k, and this is just a natural product. Okay. Now with respect to these two, this k becomes a vector space, right? Because it satisfies all the property of vector space, right? K pass is abelian group. We call what is the property of vector space? Abelian group. Okay, and then this is the operation, and then distributive property holds, right? Distributive. So this multiplication distribute over addition. Okay. So this is clear that whenever you have a field extension for over a field f, then that extension field will become the vector space of that. Okay. So naturally one can ask what about the dimension? It has a nice name here. It is called the degree. Okay. So let me define it. So let k of if I will write down this notation also. So that means k is extension b and extension of k or if, then the degree of k over f is the dimension of k as a vector space over a, right? And we write down this notation. The degree is by this notation k, or some people also write down so this is dimension of k. Okay. Some book also use this notation, only this. So generally I use this in this notation. Okay. So this is called the dimension or degree and degree of k over s. Okay. And whenever this is finite, we say this is finite dimensional. If it is not finite, we say infinite dimensional. Dimensional extension. Okay. So yeah. So this is the idea of degree. Now we would like to know that given an element, a field, and you start with a polynomial ring over that field and find out the irreducible polynomial, then can you find out some extension which contains the root of that polynomial? The answer is yes. And so before doing that, I like to just give one more remark. So you see that whenever you have a homomorphism, so any homomorphism phi from any to field f1 to f2 is either trivial. Trivial means what? Means the everything mapped to 0, trivial, or injective. Okay. So what does that mean? That means the current injective, we recall that if a map, linear map, field or whatever ring homomorphism is injective and only the kernel is 0. So what I'm saying that the kernel is either the full thing or the half thing. So that is obvious, right? So this is that is, so you can, so proof will be like that, that the kernel of phi is an ideal of f1. Okay, but f1 is a field, right? F1 has only two ideals, namely zero ideal, zero, and the full ideal, right? Clear. So when the kernel, if kernel of phi equal to f1, then phi is trivial, right? Trivial homomorphism, everything maps to 0. And if kernel of phi is 0, then obviously phi is injective 1 injective homomorphism or it's also called embedding. Okay, and if you have phi from say f1 to f2 is an injective homomorphism, then we say f1 is embedded. What does that mean? That means there is a isomorphic copy of f1 which is sitting right into f2, embedded in f2, right? Because your f1 is isomorphic to phi of f1, which is a subfield of f2. Okay, so this is just first isomorphism theorem of rings. Gives you this. Clear? So so embedding means that the copy, this is sitting as a copy inside f2. Okay. Yeah, so now the fundamental theorem, we would like to understand that whenever I have a field F and I have a irreducible polynomial about that field, can I find an extension which contains say for example a roots of that polynomial or not? And the answer is yes. So let us try to find out. Is it so? So this is important idea. This is going to help us later many places. So theorem. So let if be a field, okay, and I choose some polynomial px be an irreducible polynomial over f. What does that mean? That is a polynomial inside fx, which is an irreducible polynomial. Okay, then there exists an extension of f which contains, okay, so so extension, so you know the meaning of extension. Extension means f is in a subfield of that, right? Or rather yeah, so I must say that I should not say extension like this. So I should say there exists a field which contains f. It's also saying the extension. Okay, no problem. So which contains both are same actually, contains a root of px. Okay, so what I'm saying that no matter whatever polynomial you're choosing, whatever it is a polynomial or any field, you always find out an extension of that field which contains a root. Okay, this is very fundamental theorem, and the proof is also very interesting. So proof goes like this. As fx is an Euclidean domain, right, that we already proved. Euclidean domain is also PID, right? So also PID. So what does that mean? That means the ideal generated by Px is a maximal ideal, right? Because in a PID every irreducible element generated maximal ideal, right? So what we can show, so we can talk about the quotient ring, and by the characterization theorem, this is actually a field. Is a field, right? Clear? So this is a field. So now obviously you can ask so I mean, see, when I'm saying extension, I mean to say that a copy of, I should say that extension of f means so that is a, so I mean what I'm saying here, star, so a copy of f is sitting as a field of, sitting as a subfield. Okay, this is I mean subfield. Okay, so can I show that if I say copy which is a subfield of this? Let's see. So that is obvious. So if I can find out that f is embedded inside K, then I am done, right? So claim, so my claim is that f is embedded in K, then I am done, because that means the copy of f is sitting inside K as a field. Okay, now to show that, what I need to do, I need to find out an 1-1 homomorphism of field, right? So if you start with phi, so let me define phi from f to K by just you send any element of f. See, f is also element of, if a is an element of f, a is also element of fx, right? And then you take what is this, the image, so I can write down a bar, which is nothing but a plus this ideal, right? This is my notation. So if I define my map like this, so you can now easily check that this becomes a homomorphism. That is obviously right. So clearly phi is a homomorphism from f to K, right? Now what is the kernel of, now note that the kernel of phi is what? So this is all the a belongs to f, all the a belongs to f, such that this a bar is 0 in K, right? A bar should be 0 in K. And now you see, this is one way finding, or I can say one more thing. the lemma we proved before this theorem. So or rather the remark. Yeah, so this remark tells you that it is either trivial or injective. So see that this homomorphism has to be injective, because so kernel has to be equal to 0, only 0. So this is actually 0. Why? Because see, if I is not a trivial homomorphism. Why? Homomorphism as the identity that maps to identity, right? Here, say identity is 1 plus this 1 plus px, which is the identity inside K, right? So obviously the image is not 0 here, so this cannot be a trivial map. And the previous remark tells you that if it's not a trivial map, it has to be 1 1. So that means phi is injective. Okay, so the moment you have injective map, then you just prove that thus if is isomorphic, whatever the symbol you write down, to phi of f, which is sitting inside a subfield, which is a subfield of K, right? So this one is obvious. So you find out a kind of extension which contain f, right? And now I need to find out, now my claim is that K contains a root inside of the universal polynomial P, right? Now note that you have x bar, right? X bar equal to x plus this is in K, right? Because x was inside f, so x bar is inside K. And what is the value of P of x bar? So P of x bar is nothing but Px whole bar, right? As this so this bar is coming from the canonical map. So you always have a canonical map here, right? From okay, so let me write down here also, right? So from fx to fx mod this, which is K, it have a canonical map, right? So any polynomial you are sending it to f bar, right? So f bar means that this, right? So this is a homomorphism also. And if you evaluate this element on this polynomial, it becomes Px bar, right? As this is the canonical homomorphism, right? So yeah, whatever, you can write down this is a polynomial and then take bar, and bar will goes to inside this, right? Whatever. So this is this, and then you can write down this. This is nothing but Px whole bar. So what does that mean? Px whole bar means it is actually congruent to Px mod Px, right? Because I am going to the ideal modulo Px. So what does that mean? That means it's congruent to 0, right? Mod Px. So this thus this Px bar equal to 0 mod this, okay. So x bar is a root of P in K. This is the proof we want. So we just proved that you have a field which contains f. Not only that, it contains a roots of Px also. So no matter whatever irreducible polynomial you choose, you can find out a bigger field which contains the root. Okay, so this is a very mm, very fundamental theorem. And now question is that how do I write down this kind of extension? Like do I have a proper way to express these elements? The answer is yes. So because as um, k whatever, write it down, over if is a vector space. So we can write down. So we have it's not only vectors, but this is actually finite. We will show that this is finite dimensional vector space. We have a basis. We have a basis of k over f. Okay. Now what are those things? So for that, let me just write down, let us say degree of my px is something, say choose something, say m. Okay, and if you have a MD polynomial, and then what you do, you just write down this. Your alpha is the image of x in k. So what does that mean? That means alpha equal to x plus this px in k. Then my claim is that the set is containing 1 alpha square and dot alpha to the power m minus 1 forms a basis of k over f. Okay, this is my claim. So it has a basis. So once you have basis, you can write down the element in linear combination of these vectors, right? Basis vectors. Now how do you find out the proof? How do you know that it has a basis? This is a basis over that. So to prove something is a basis, what you need to find out? You need to check that this is 1 1 and 1 2 or not, right? So anyway, to check something a basis, you need to check this is linear independent and generating set, right? Spanning set, whatever. Or these two things we need to check, right? So so one part is obvious. Both are obvious, not so difficult. So we can easily prove this claim. So let me prove that this is a linearly independent set. So how do you prove this is a linearly independent set? So on the contrary, so I'm using the method of contradiction. Let S is not linearly independent. Then what happened? Then there exists some constant c0, c1, then cn minus 1, whatever. So you can find out the constant that is over f, not all 0. This is very important property. Not all of those things 0. Okay, and 0, and they satisfy what? Satisfies this condition. What is the condition? Condition is that C0 plus C1 alpha plus C2 alpha square, right? What was Cm minus 1, not m minus 1. M minus 1 and Cm minus 1 into alpha m minus 1 is equal to 0, right? But what does that mean? That means C0 plus C1 x bar plus C2 x bar square and dot 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 Cm minus 1 x bar m minus 1. This is 0, right? 0 means 0 in K, so the modulo that ideal. And this is what? This is nothing but C0 plus C1x plus Cm minus 1 x, okay, plus this, right? So this is 0 mod 0 in or 0 mod this polynomial, right? So what does that mean? But this is part of this, right? So what does that mean? That means these polynomials C0 plus C1x plus m minus 1 Cm minus 1 x by m minus 1 is congruent to 0 mod px. So this implies px divides this polynomial, right? And which is a contradiction, because px is a polynomial of degree m and this is a polynomial of degree at most m minus 1, because Cm minus 1 may be 0 also, I don't know. So degree can be at most m minus 1. So which is a contradiction, which is a contradiction. Okay, degree as degree of px is m, right, which is bigger than m minus 1. So at least this has to be at most m minus 1, the degree of this polynomial, but px has more degree, right? So what does that mean? Thus S is a linearly independent set. Okay, now can I show this is a generating set or spanning set or whatever, and that is also we can easily show. So to show something is a generating set, what we need to show? We need to show that any polynomial or any element of K can be written as a linear combination of those elements, right? Now if we choose any element, so how this look like any element? Now to show S is a spanning set, you choose any polynomial, say fx belongs to capital Fx, okay? And I know that the image of this under the map, that natural canonical map, it's element of K, right? Now if you choose any element Fx, then the Euclidean algorithm, see, because Fx is Euclidean, right? The Euclidean algorithm gives you, what do you get? You will have Qx and Rx belongs to Fx, such that what happened? You can write down Fx equal to Qx times Px plus Rx, okay, with either Rx equal to 0 or degree of Rx is less than degree of Px, right? This is the equivalent algorithm gives you. Okay, so thus your Fx is nothing but congruent to Rx mod Px, right? So modulo Px, they are Rx, right? So what does that mean? That means any element that you can write down in terms of a polynomial which has degree less than that, right? So what does that mean? That means if you choose an element, so that will be so these elements, so they are coming from quotient of a polynomial, right? So those polynomials are congruent to a polynomial whose degree less than degree of p, which is m, right? And yeah, so this is my m, so less than m. So thus any element of k, which is nothing but Fx mod Px can be the thought of a polynomial in alpha of degree less than m, right? So what does that mean? That means is a spanning set for k, right? So what does that mean? That means you can write down k as like some a0 means a0 into 1 plus or rather you can write down, no, let me write down a0 a2 a1 into alpha plus a minus 1 into alpha m minus 1, okay? And this ai is an element of f. So you know that element of k is of this form, right? So you can explicitly find out how this element look like. Clear? So and obviously you can ask then with the help of these spaces, how do I add or multiply those things? So this is almost obvious. So okay, so one more thing, yeah. So this is okay. Yeah. So now observation that so if you choose two elements, for example, so choose two elements, A and B belongs to K, and then obviously you know that A will be some function of alpha and B will be another function of alpha, and then if you add A plus B, and this will be nothing but these sums, right? Summation AI plus BI into alpha power I equal to 0 to a minus 1, right? So this will be sum. But product is interesting. Product, if you want to take product A into B, so you have to take first alpha A and beta alpha, sorry, A alpha beta alpha, and then you have to go modulo something. So suppose this is modulo something C alpha, this modulo Px. So if it is modulo Px is A alpha, then you can write down this is C alpha. Okay. So your question is, how do I get this alpha? So you just go, you take Ax and Bx and then do this multiplication and then quotient out by Px, then Rx or Cx will be the remainder, and then put C alpha. So that would be that product. Okay, maybe I will give an example, then you will understand. Okay, so now let me give an example that is very essential, that how do you find out field of complex number from the field of real numbers. Okay, so in this case our field f is nothing but field of real numbers. Okay, this is field of reals. Okay, and my px equal to say x square plus 1. And there are many ways of constructing that, but I'm taking this fx. Yeah, so now note that this is an irreducible polynomial, so which is an irreducible polynomial in R as PS has no roots in R, right? Because if it has a roots, then the square of that element has to be negative -1, but square of every element in R is positive always, right? Positive or 0, so it cannot be negative. So this is an irreducible polynomial. Okay, so thus to define this the complex number C by this, the polynomial ring over R, and then go modulo this ideal x square plus 1. Okay, clear? So this will be a field because R is a field. So you have irreducible polynomial, that will be maximal ideal. If you go by maximal ideal, you have a field, right? Now question is that how do you define these roots, these elements, right? As you know that I define my alpha is this x bar, which is x plus this ideal generated by P, okay, which is nothing but x square plus 1 here. And now so we can write down this element of C as of the form A plus B alpha. Okay, where A and B are element of R. Now what is the property of alpha? So alpha satisfies the equation. Now note that that P of alpha equal to 0. That we already proved that alpha, the x y z roots of this, right, is 0. So alpha square plus 1 equal to 0. Okay, so sometimes you can people write down alpha equal to -1 something, whatever, and we write down this alpha, we use this notation iota, which is to the power of -1. This kind of this notation people use. Okay, so no matter. So now if we have this kind of A plus B alpha is the element of this, and then you can easily, first of all you can add it. So addition will be nothing but say A1 plus B1 alpha, and then you have A2 plus B2 alpha, and that will give you A1 plus A2 plus B1 plus B2 of alpha. Okay, this is a simple addition, and the multiplication will be again the modulo that polynomial. Okay, x square plus 1. So how do you multiply? So A1 plus B1 alpha and sorry, A2 plus B2 alpha. Now you multiply, if you multiply 1 by 1, so A1 A2, and then A1 B2 of alpha, and then B2 A of B1 A2 of alpha, and then B1 B2 of alpha square, right? Now you see that alpha square equal to -1. See here, from here, which is a real number, right? So you have to replace that. If you replace that, then what happens? Then it will be A1 A2 minus B1 B2 plus A1 B2 plus B1 A2 of alpha. Okay, so this is a multiplier, right? So in another way, you can write down this is some kind of vector space, right? So you can write down tuples A1 A2, sorry, A1 B1 and A2 B2, and then multiplication will be what? So if you multiply this thing, it will be A1 A2 minus B1 B2, and the second quadrant will be okay, 1 minute. So yeah, so A1 A2 minus B1 B2, and this will be A1 B2 plus B1 A2. So A1 B2 plus B1 A2, and this is the complex multiplication actually, right? The usual complex multiplication. So this is the map, and if you feel that okay, how do I think this is C, you can start with something K and then C, and then obviously you can have this natural map, right? That are natural isomorphism. So you can easily define the natural. When I say defined by these, I mean that you take alpha and map it to iota. Then you are done actually. These maps. So what does that mean? That means A plus B alpha is mapped to A plus B iota, and that will become, say, isomorphism of rings. So morphism of rings, or other field, I should say, isomorphism of field. Okay. Okay, so maybe I will stop here. That's this introductory part of field theory, and later on I will give more examples and more of basic theory. Okay, so I'll stop here.